So in pre-calculus, you have really easy area formulas, right? You have triangle, 1/2 base times height, rectangle, base times height, trapezoid, 1/2 height, base 1, base 2. So you have all these formulas for these stagnant figures, polygons that you have learned your whole life. You know what these polygons are. And then all of a sudden you get to a calculus world, and you can think of pre-calculus as like stagnant and calculus as movement, okay? And so all of a sudden we now want to know the area under this curve. Well, this is not a perfect geometric figure. It's not a circle. It's not a semicircle. This is just not a perfect little world that we can just plug in a formula for. And so what they started doing is they said, well, let's just make it with things that we know underneath it, all right? So they started out by just putting in rectangles, right? And they said, well, this is going to approximate the area, right? The problem is we have this part that's on the outside that's too much, and then we have these empty spaces here. And so they said, well, we'll just do more rectangles. So this was only 3 rectangles. Let's do 5 rectangles. And you can see that we have less space sticking out and we have less space left over. And then look at this one. When they did all of these rectangles, you can see we're getting closer and closer to the exact amount underneath there. There's just a little tiny pieces right here that are sticking out and little tiny pieces here that are missing. And so you can imagine if we did 100 rectangles under there, we would be even closer to the actual amount. And what you'll find is that we use limit theory here. And so then limit theory, as it gets to the number of rectangles moves towards infinity, then you actually have the area under the curve. And so anytime you start using limit theory with infinity, you're moving into calculus, all right? And so you move from the stagnant, 5 rectangles to a limit theory here. And this is the limit theory that says the area of the region under the graph of the function is the summation. We'll start with that notation first because y'all know this notation. This notation means added up, right? We just did this in the last chapter. The summation of all these rectangles created by this function all the way to infinity. So if we were to take this summation to infinity, like an infinite series here, you get this. And then they introduce this notation right here. And this notation right here is integration. And so what they found is when they started doing this limit theory, it actually lined up with derivatives. And so the derivatives gave you the function, and what's called an antiderivative gives you this right here, this area under the curve. So derivatives give us a ton of things. They give us the slope of a tangent. They give us our maximum and minimums. They also can give us things like if we have the position function, we can find the velocity and the acceleration. That's what derivatives tell us. And then with integration, the first introduction that you get to integration or antiderivatives is the area under the curve. I have this function and I want to find out what the area is under that curve. If I were to need paint to paint under the curve, how much paint would it take to cover that area? And that's what integration helps us do. And so next year we will actually use Riemann sums to do it. This year we're actually going to jump straight to the fundamental theorems of calculus, all right? So switch to then section 6. So we have found derivatives. You'll recall that finding derivatives is you take the exponent, you multiply that in front, and then you subtract 1 from your exponent to get your new exponent, all right? Antiderivatives exactly go the opposite. You take the exponent and you add 1, and then you divide by your new exponent. So you're just working back into the original function. So we have been given the original function in the prior sections, and we have found the derivative. Now we're going to be given the derivative, and we're going to be finding the original function, all right? So we're just working our way backwards. Think of it as multiplication and division, right? They just undo each other, all right? If you have a constant in front of it, you will just divide. That's going to be part of your division. And if you have different functions added together, you just take the antiderivative of them individually. So let's look at these first, and then we'll apply them. Find the antiderivatives, okay? So this is no longer derivatives. We are working the other direction, all right? And the notation that you will see sometimes looks like that. That means find the antiderivative. That is integration. All right, so if we're finding the antiderivative of this, we're going to take this function, and we are going to add 1 to our exponent, and then we are going to divide by that new exponent, all right? So we have 4x to the 8th over 8, and we can reduce that, so we get x to the 8th over 2. All right? And then you'll notice when you do antiderivatives here, a couple things with notation. They actually use this capital letter to indicate that you found the antiderivative of a function. And then they also add this constant at the end, all right? Why do they do this? Well, what happens to constants when you take the derivative? They turn to 0, right? So while x to the 8th over 2 represents the antiderivative, you have to consider that there could have been any constant added to that antiderivative before you took it. And so you just have to account for the fact that, hey, I could have had a 1 or a 2 or a 3 or a 4 or any constant added to that function, and it would still give me the same antiderivative, right? So if I had taken something like this, 3x squared plus 2, what's that derivative? How do I find the derivative of this from my prior sections? 6x, right?
Yeah.
What about 3x squared plus 7? What's the derivative? What about 3x squared plus 422? All right, so do you see how you have to account for the fact there could be a constant? And that's what this C represents when you take the antiderivative. You take the antiderivative, then you have to consider, they haven't given me any other information. If they had given me more information, there are times when I could figure out what that C is. But if they don't give me any other information, I have to account for that constant. All right? Let's look at the next one. All right, for some of these, just like derivatives, you want to rewrite them first. So before I take the antiderivative, I'm going to write this one as 2x to the negative 4. All right, 2x to the negative 4. What is my new exponent going to be here? 2x to the, I have to add 1. Negative 4 plus 1 is? Negative 3. And I divide by that new exponent, all right? And then you want to make this mathematically correct, okay? So I'm going to say, well, that's going to be 2 over negative 3x cubed plus c. All right, so you do want to put it back in the denominator when you do this, all right? And then let's look at the last one. I add 1 to my exponent, so it's going to be x to the third divided by 3 minus 8x to the second divided by 2 plus 5. What's my exponent here on this x? There we go. So it's just 5x. Anytime you have a constant, when you're taking the antiderivative, it's just going to be the constant times the variable. All right? You do want to simplify this. You'll sometimes see it written like this, 1/3 x cubed. If you can reduce. So that is 4x squared, 5x plus c.
That makes sense.
C.
For the constant staying in there.
Yes.
X before it.
Yep. So for this second one, you have to divide by your new exponent. So your exponent here is, it's going to be 10x to the negative 3. So your new exponent is negative 2, and then you divide by negative 2. So you get negative 5x to the negative 2. And I would actually want you to rewrite this, negative 5 over x squared plus c.
Oh, wow, I forgot this.
So the first thing I want to talk about in this problem is you have to know a relationship between your functions. And you've probably talked about this in physics, but now we're looking at from a calculus side. So you have functions that deal with where things are. And so the first function that you always deal with is your position function. This is often used like if you hit a baseball, all right? And the height of the baseball would be your position function, all right? It's actually going to Like a baseball, think about when you hit it, it's going to cause a curve. Or if you throw a football, right, it's going to curve and it's going to come back down. Okay? And so that position function tells you where, after 2 seconds of releasing the ball, what height the ball is at. Okay? That is your position function. All right? And then your first derivative of your position function. So when you have a position function, if you take your first derivative, you will have your velocity function. How fast is this thing going after 2 seconds? So position function tells you where it's located in the air, height, or whatever the function is telling you. The first derivative of that tells you how fast the ball is going. All right, and then the derivative of this guy, or second derivative, but if I take this and take the first derivative of velocity, I get my acceleration function. All right, and acceleration tells you, right, how it's changing, okay? And so when they start giving you velocity and position functions, they are actually talking about derivatives of each other and antiderivatives of each other. So for example, if they gave me the acceleration function and they wanted something to do with velocity, I could take the antiderivative of my acceleration and I could find my velocity function. If they gave me my velocity function, I could take the antiderivative of that and find my position function, okay? Because they all work together. So it says students of Miss Nair's technology class are participating in an egg drop competition. Each team of students must build a protective device that will keep an egg from cracking after a 30-foot drop. The instantaneous velocity of an egg can be defined as V of t equals negative 32t. All right? Where t is given in seconds and velocity is measured in feet per second. All right? So find the position function of the egg. Well, they have given us the velocity function. Velocity function is negative 32t, which means the position function is going to be the antiderivative of that. So what is my exponent here? It's going to be negative 32t what? It was to the 1, so now it's to the 2. We are taking the antiderivative over 2. Negative 16t squared plus c. Negative 16t squared plus c. Now, it actually told me my initial position. Did it not? What is the initial position of the egg? 30 feet. So they actually told me what happens at s of 0. At s of 0, I am at 30 feet. Everybody agree with that? At 0 seconds, I'm at 30 feet because I have not dropped the egg yet. So I can actually plug in this guy and figure out what c is. If s of 0 is 30, that means negative 16 0 squared plus c equals 30. Right? Does everybody agree with that?
Yes.
If my initial position is 30, I can plug in 0 and figure out that c is actually going to be 30. And that's what it will always be in your position function, by the way. Your initial starting height will be that constant in your position function. So now I have an actual function here. My function is going to be negative 16t squared plus 30. All right? That's what my function is going to look like. And so now they said, the second question is, how long will it take for the egg to hit the ground? What height are they looking for when the egg hits the ground? What's the height of the egg when it hits the ground? How many feet off the ground is it?
30 feet.
When it hits the ground, it's 30 feet off the ground. It's 0, okay? So, I'm looking for where my position is. So if I want to know how many seconds it will take to hit the ground, I want to actually set my height function, my position function, equal to 0. That's when it hits the ground. And then I solve. How do I solve for this?
Subtract 30 over.
Subtract 30. Yep.
Divide by negative 16.
That's right.
And then do the square root.
Right. So t is going to equal the square root of 30 over 16, right? Which gives you approximately 1.369 seconds. So we've been doing indefinite integration, which means that you are just finding a new function. We've basically just been saying, okay, here is this one function, find the new function that represents the antiderivative of it. The first fundamental theorem of calculus then moves to that area under the curve. It says, well, if you know the beginning and the ending points of the area that you're trying to find, you can use antiderivatives to find the actual area under the curve. And you can do that by taking the antiderivative and plugging in the top bound and then subtracting that from what happens when you plug in the bottom bound. And that gives you the actual area under this curve of whatever function you have. And so they give you some notation here. The notation, this first notation means integration. So when you see this little S type thing that reminds me of like music notation or something, they've given you saying, I want you to find the integration from A being your lower bound to B being your upper bound of this function. And when you find that, you'll actually be finding the physical area under that curve. So let's look at example 4. Use the fundamental theorem of calculus to find the area under the region of the graph for each function. And so they've given us this graph over here. The function of the graph is notated right here, 4x cubed. And they are wanting us to go from specifically 1 to 3. So that means they want us to find this area right here. What is this area? And so prior to calculus, we would have had to estimate it almost like a triangle. But you can see it's not a triangle, right? We have a curve there on the side of it. And so there's a couple things you need to notice. Y equals 4x cubed, that gives us the function. 1 to 3 gives us the interval. The other way to write that looks like this. Integration of 4x cubed from 1 to 3 with respect to x. Next year, we will do integration with other variables, but right now they're telling us you are integrating it with respect to your x variable. So your boundaries will be your x boundaries, and all of your variables will be x's in this, okay? And so what we're going to do is we are just going to take the antiderivative of this 4x cubed. What is my new exponent? 4x to the, we're doing antiderivative, 4x to the 4th, divided by my new exponent, right? I reduce that how? So it's just 4 divided by 4, so it's just x to the 4th. And then you write this notation here from 1 to 3. The way you solve for that area is you plug those in. You plug in the top number first, 3 to the 4th.
What about C?
Minus 1 to the 4th. There is no C because it is definite integration, okay? Definite integration has my endpoints on there. And so it is not an indefinite integral. It actually has boundaries. So I don't need a C. I'm going to get an actual number here. So this will give me 81 minus 1. The area under that curve is 80 square units.
Is that it?
All right, antiderivative. So we have this function here. They want us to do integration of negative x squared plus 4x plus 6 from 0 to 4. So we are going to do the antiderivative. Negative x, my new exponent is 3. And so we're going to put that over 3. Plus 4x, my new exponent is
2.
Over 2. Plus 6x. So we will reduce this as much as possible before we do this. 2 ways to write it. Sometimes they write negative 1/3 x and sometimes they just leave it. I don't care which way you do it, but you do need to reduce this guy here. And we are doing that from 0 to 4. All right, so we're going to plug in a 4. When we do that, we get negative 4 cubed over 3 plus 2 times 4 squared plus 6 times 4 minus, what happens when I plug in a 0 to those? So this is my B, right? Minus 0 over 3 plus 2 times 0 plus 6 times 0, right? So this is just 0. All right, so that's not going to affect it all. Now, if 0 is in the top, it does affect it because you're subtracting. You always subtract those two. But when it's in the bottom, it actually doesn't affect it that much, all right? And then we're going to just do it. 4 cubed, what is 4 cubed? Yeah, negative 64 over 3. 4 squared is times 2, and then plus 24, right? If you get a common denominator, and I don't know if they wrote it in decimal form, they just wrote it in decimal form. So when you do this in round, 34.67. Area under that curve is 34.67 square units. All right. So go ahead and try A and B there. Basically, this just tells us the difference between indefinite integration and definite integration. Indefinite integration, you will notice, does not have a bottom and a lower and upper bound here. There's nothing on your integration. See, there's no numbers. So when you see this guy, you will have a plus C, and you'll just have a new function. On B, you notice you have a lower and an upper bound. This will give you a numeric answer, okay? So A is going to give us a new function with our plus C, and B is going to give us an actual numeric answer, all right? So for like this first one, we would say this is going to be 9x squared over 2 minus x to the 4th over 4 plus C. That is my answer here, okay? But for this second one, it is the same exact integration, 9x squared over 2 minus x to the 4th over 4. We do not have the plus C, and we actually plug in 2 and 3. And so you do need to know the difference between the two, because one is going to actually give you an answer, and one will give you just a new function.